Okay, let's continue. In the last class, we started to see how we can stabilize our multi-stage op-amp, and we started with the goal of looking at a two-stage OTA, and we essentially saw that there are two schools of thought. One is to try to go and introduce a left-half plane 0, so that for large values of the DC gain, the closed loop poles fall back on the real axis. The second approach was to keep the open loop poles as far apart as possible, so that once again the closed loop poles will be on the real axis for very large values of the DC gain. And as you guys rightly pointed out, this is something we saw with Miller effect, wherein earlier we had two poles close enough. After we included the Miller effect, one pole shifted to a high frequency, other moved to a low frequency. So let's quickly refresh that result, and then we'll see how we can use it to stabilize a two-stage OTA. And in which context did we first encounter Miller effect? In which context did we encounter Miller effect? Okay, if you recollect, we were looking at a common source. So if I draw the common source, this is input. I considered a source resistance. So here the gate of the transistor was there. We'll replace it with the OTA for simplicity. And here I'll draw the gate capacitance C1. And let's say at the output I have something, say some output conductance, output capacitance. So here in this config, for this, what are the pole locations for this circuit? What are the pole locations in this? Yeah, so I'll write it as conductance GS by C1. Second is G2 by C2. This is clear. And then we considered the capacitance across the conductor, transconductor. We'll call it C. So again, remember, just want to clarify that if you take a simple common source like this, the capacitance across the input and the output of the transconductor is the capacitance across gate and drain. In practice, this gate to drain capacitance is actually very small, and the most dominant parasitic capacitance will be that from gate to source. Okay. So if you just take a simple common source, the Miller effect will not be that pronounced, but let's assume that we are going and putting an explicit capacitor for now to see this Miller effect. Okay. So let's say I put an explicit capacitor C now. Now we know that we have a capacitance across an amplifier. We can use Miller effect, but we can use it exactly if you know the true voltage gain from the input to the output. That would have been possible if we had a voltage controlled voltage source, but this being a VCCS, we do not know the exact voltage gain from the input to the output. But that's when we decided to do an approximation that we look at low frequencies wherein the capacitors can be considered open, which means if the capacitors are open, what can you say about the low frequency voltage gain? If I call this GM, what is the very low frequency voltage gain from the input to the output? Minus GM by G2. So then we saw that this capacitance then can be reflected at the input side, capacitance times the gain. So the low frequency pole, we can approximate it this way. First let's write the total capacitance. So what will be the total capacitance here? What are the capacitances you see now? I have C1, and what else will be there? C will be reflected with that gain. So total will be C1 plus C into 1 plus GM by G2. And what is the total conductance you see at this node? What is the total resistance you see in this node? RS. So the conductance is basically GS. Similarly, we also can write the high frequency pole intuitively. And for the high frequency pole, we essentially look at the total conductance and capacitance at the output node. Again, for high frequencies, we can say that, first of all, pole calculations, input is short. And at high frequencies, we argued that the capacitor will offer a much lower impedance compared to the resistor. So which means we don't have to consider this fellow for high frequencies. So if I look at the output, I have this capacitor C2 that comes in parallel with series combination of these two capacitors. So total will be C2 plus the series combination of C and C1. Just this. And we can similarly write the total conductance. So at the output node we have a conductance G2, so that we can write it directly. But in addition, what other component will contribute to the conductance? Yeah, if I apply a test voltage here, what will be the portion of the test voltage appearing here? Vt into, I mean, if let us say this is a test voltage you apply, how much of that will apply here? C by C1 plus C, right? So which means, what can you say about the current we draw here? Yeah, the voltage here is this much, so the current that GM draws is proportional to that. So this will also produce a real part of a current when you apply a test voltage. So that will also contribute to a total conductance, and that value is essentially GM. Let me erase this, or let it be there. So as we saw, this one pole moved to a low frequency, other pole shifted to high frequency. This is something we'll refer to as pole splitting. Cool. So this is something we saw with Miller effect. Let's see how we can exploit this to stabilize our two-stage OTA. Well, for that I'll erase all these so that there is not too much info. So first let me sketch a two-stage OTA. So I have a first stage, one GM. Let's say that is GM1. At the output we have effective conductance G1, capacitance C1. And let's say I have a second stage. So let's say that is GM2. And at the output I'll consider the intrinsic conductance and the load conductance. Together I'll call it as GL prime. Similarly, I'll club both the intrinsic capacitance and the load capacitance. I'll call it as CL prime. So this is your two-stage OTA if you cascade two of them. So as such, if you have this structure, where are the poles located? Sorry? G1 by C1 and GL prime by CL prime. Again, these are uncoupled time constants, so we can directly write it. So this is G1 by C1. Second pole is GL prime by CL prime. Again, remember, although we have a load capacitor which typically might be large, so CL prime will be very large. Okay, but the issue is we have a two-stage OTA for driving a resistive load, so we can have a small RL, which means GL will be large. So in the second pole we have GL to be larger and CL prime to be larger. So these two poles might not be so far apart. If let us say we didn't have GL at all, then we have G2 by CL. Maybe we can argue that CL is large, so maybe this G2 by CL might be at a low frequency. But if you also have a load resistor, you can no longer argue the same. So again, the poles are now close enough. This is not great because you want them to be spaced as far apart as possible. So let's see how we can exploit Miller effect here. And for that, I'll just modify the common source here slightly. So if you notice here, I have a voltage source Vin in series with a resistor Rs. So how can I transform this as current source in parallel with the resistor? What will be the value of the current source? Vin by Rs. So I'll write Vin times Gs. So I can redraw this like this. I have the conductance in parallel and I'm essentially injecting a current, just V in times ds. So now let's look at start at a two-stage OTA. Here this is the input. What is the current that is fed in here? GM1 V in current. So now if you look at the two circuits with respect to the pole calculations, again the V in is 0, so the current source is open. Again for pole calculations, V in is 0, this fellow is open. So you essentially have a very similar structure, right? So here again we have a similar case. We had poles that are close enough. To split these poles, what can you do now? Across? So here as we saw, if we added the capacitor across this transconductor, the pole split. Here this is essentially this fellow. So you basically go and put a capacitor explicitly across this. We'll call it CC. CC stands for compensation capacitance. Again, in general, this entire business of making the closed loop system stable by changing some things in the poles and zeros is called frequency compensation. Okay. So now if I do that, let's quickly write the pole location. So what will be the low frequency pole now? Help me write the low frequency pole. So what is the total capacitance here? C1 will be there. In addition to it, what else will come? Yeah, CC times the low frequency gain, which is GM2 by GL prime, right? So let's write the capacitance. C1 plus CC times 1 plus GM2 by GL prime. Okay. And what about the conductance at this input node? Only G1 is there. Similarly, let's look at the high frequency pole. Again, for high frequency pole, same arguments. You look at the total capacitance here and you can ignore this resistor in comparison to the capacitor C1. So if I look at the total capacitance here, I have again CL prime and these two fellows in series. Okay. These two, I mean CL and the series combination in parallel. So I'll have CL prime plus C1 CC, right? Similarly, if I write the total conductance, I obviously have this GL prime, and what else will come? Yeah, we'll have a portion coming from GM2, and what fraction of GM2 will contribute to current? CC by C1 plus CC. So I'll write it like this: GM2 into so hopefully now you should be comfortable in intuitively writing the pole locations in this case, right? You don't necessarily have to remember it. Just by inspection, you can hopefully now write the pole location. Cool. So now this is good again because this has shifted to a low frequency. This has moved to a high frequency. So on paper we have accomplished what we wanted to do. But in this process of splitting the poles, have we introduced an uninvited guest? Huh? Yeah, remember we have looked at poles. Yeah, the two poles have become far apart. But we also have a 0 because I can short this capacitor here CC. The output will still be non-zero. I mean, I cannot short C1 or CL, but I can short CC, the output will still be non-zero. So we have one 0. So let's see where that 0 is. So we'll just erase this portion. Again, for 0 calculation, the same thing we do. We assume that the out in the Laplace domain is 0. And let's try to write KCL. Let's write here, and intuitively also we can see, right? So from the input to the output, we have two paths for the current to flow, one through CC, one through the transconductor GM. these two currents will have different frequency dependence, so they can add up to 0. So if I call this voltage as some V1, what can you say about the capacitor current? I mean, we don't write in time domain, right? Yeah. So V1 of S times SCC. What about the current through the GM? Minus into V1 of S. Sum of these two will be equal to 0 because the output is assumed to be 0. So again, we can argue that V1 of S cannot be non-zero because you are applying a finite input, a non-zero input. So which means the only possibility is for the complex frequency S to take this value GM2 by CC. So this is at left of plane or in the right of plane? RHP 0. So from whatever you know so far, this is good or bad? This is really bad. So which means our phase margin is not going to be so great. This will take a hit. So let's see how much the phase margin will be.
Would there be no current through C1?
I mean, C1 will take a current, yeah. We are writing the KCL at the output node, right? Sum of these two currents is equal to 0. Okay. I mean, we are looking at the output node. I mean, that's why the current through GM2 is coming, right? Okay. Sum of these two currents is equal to the currents in these two. These two carry 0 current. So let's look at the phase margin, but before that, let me just summarize the result once again. So where is all this? Yeah. So what we have here is typically called the two-stage Miller compensated OTA. So let's write down all the properties of this fellow we know. So what is the DC gain of this two-stage OTA? What is the DC gain? Yeah, DC gain is where you don't consider the capacitors. It's GM1 by G1 times GM2 by GL prime. That's the DC gain. So let's write the pole zeros. So tell me again, let's again write the pole location so that you get used to this. The low frequency pole is how much? I look at the total capacitance here. How much is that? C1 plus?
1 plus GM2.
Yeah, 1 plus, let me write it, CC times that gain. 1 plus GM2 by GL prime. And what is the conductance here? G1. Okay. And remember, in practice we will have this gain to be sufficiently large, second stage gain. So this is gain multiplied by a capacitance. So how can you approximate the denominator as? Yeah, remember C1 is a parasitic capacitor. CC is an explicit capacitor that you are going and putting, and that seems to be multiplied by a gain. So the denominator you can further approximate for practical purposes like this, CC times Similarly, let's write high frequency pole. So what is the total capacitance at the output node? I have CL prime and these two fellows in series, right? So I have CL prime in parallel to the series combination of C1 and CC. Okay. And what about the conductance at the output node? We will have GL prime.
C2 times CC by CC.
Yeah. we have GL prime and combination due to GM2. So this is GL prime plus the capacitive division you have for GM. Okay. Now let's again tell me here in the numerator I have GM2, I have GL prime. So which of these two terms do you think will dominate in practice? GL term or GM2 term? GM2 term, because GM2 by GL you want it to be much greater than 1. GM2 will be much greater than GL. So again for practices, I mean for practical purposes you can approximate it this way. Correct. Yeah, GL prime will be large. That is, load resistance will be small. But you design your second stage accordingly so that you have sufficient gain, right? I'm not saying this is going to be 1000 million, but this will at least be 10 or 20 or something. Right? Okay, so let's say I give you further information that the parasitic capacitor C1 is much smaller than Cc. Then how can you approximate the numerator as? If C1 is much smaller than Cc, what will happen to this term? 1. So numerator becomes GM2. What will happen to the denominator? I have CL prime. So I'll write it as CL plus C2. So this is CL prime by the way. So what will happen to this term? C1 is much smaller than Cc. So C1 plus Cc will be what? Cc. So this is not there. So Cc will cancel. You end up with C. So once again I also say that this is smaller than CL also. So what I am saying is C1, C2 are all smaller than CL, which typically can be the case. So how can you further approximate the second pole as? That's it. So this is assuming C2 is smaller than CL and C1 is smaller than CL. So under these two conditions is where you can approximate it like this. So please be wary of when we are making the approximations. So for this fellow, oh, that is fine, because remember we are driving this with an ideal voltage source. Even if there is a parasitic capacitance at the first stage of the GM, it's okay as of now. Okay, but this will have an effect when we see later, but as of now, since I am driving it with an ideal voltage source, it is okay. There I considered a resistor. That was a fabricated situation to illustrate Miller effect. Cool. We also saw we have a right of lane 0, so that was at plus GM2 by Cc. Right. So we have 2 poles and a 0. So I can write the transfer function as the DC gain times the RHP 0 and 2 LHP poles. Right. Now let's see what will be the phase margin. And for calculating phase margin, what is the first thing I have to compute? The unity loop gain frequency. So let's calculate that. So I'll erase this. Hope this is. So let's assume that this is the transfer function of our two-stage OTA. I'm using it in a feedback loop with a feedback factor of beta. Then what can you say about the loop gain function? What is the loop gain in terms of these two? No, that is the closed loop gain. What is the loop gain? Beta times. Right. So to find the unity loop gain frequency, you substitute S as j omega, put the magnitude, equate it to 1. So once again you will get a long equation. Engineering you should feel very ashamed. So because that's not going to yield you anything. Let's see how we can practically get a useful result. For that, let me quickly sketch the magnitude plot roughly. This is the magnitude of the loop gain. It starts with a DC value. You get the low frequency pole, and then you have this, and then you have the second pole coming later, right? And remember, this is what we wanted. We wanted to make sure that around the unity loop gain frequency, the system behaves like a first order system. Again, the reason is we know the first order system has the maximum phase margin. We try to do a lot of things to make our multi-stage system behave like a first order system, at least around the unity loop gain frequency. So if this is the case, can you approximate A of S till the unity loop gain frequency? Can you tell me how can I approximate A of S? We'll ignore the 0 on the non-dominant pole, so which means this is like a first order system. Done. This is again till the unity loop gain frequency. This is in general true for any well compensated system. I'll write it, say this is a well compensated system, which means this behaves like a first order system till the unity loop gain frequency. So now things are simple. I have a first order system. So what is the unity loop gain frequency now? I have beta times this, right? I am trying to find where this fellow drops to unity. So if I am looking at unity loop gain frequency, how can you further approximate this as S by P1? So this term is ignored. So which means what will be the frequency at which this becomes 1? Yeah, A of S becomes unity at A0 times P1. So the loop gain becomes unity at beta times. Again, this is something we saw earlier also, but you can quickly get the result even if you don't remember. So let's put all the numbers. I have A0, I have the dominant pole. So GM2 by GL prime and GM2 by GL prime cancel. G1 cancels. So I'll end up only with GM1 by CC. Okay. So let me mark that here. The unity loop gain frequency is roughly beta times GM1 by CC. Okay. And if I were to write the unity gain frequency, that is the frequency at which the A of S magnitude becomes unity, that is simply GM1 by CC. Okay. When I include the feedback factor is when you have the loop gain, so that gives the unity loop gain frequency.
So can you repeat once?
Huh?
Did we approximate A0 equal to 1?
No, we didn't. A0 is not made equal to 1.
How did we get GM by
Oh, I mean you substitute these values, right? You take the product of these two. This is A0, this is P1, right? I'm taking the product of this. GM2 by GL prime, GM2 by GL prime cancel. G1 cancels. I just taken the product and written it. Okay, so now we have the results. Let's write the expression for phase margin. So let this be here. Okay. Yeah. Okay. So I know the unity loop gain frequency. To find the phase margin, what will I do first? I mean, to find the phase margin, what value you will look at? I know the unity loop gain frequency. I look at phase at that frequency, right? So I look at the phase of the loop gain at the unity loop gain frequency. So that will be contributed by both the poles and the RHP0. Now what can you comment about the phase contributed by the low frequency pole at the unity loop gain frequency? I'll show the magnitude plot. The unity loop gain frequency is here. The lower frequency pole is here. What can you comment about the phase added by this pole at this frequency? Roughly minus 90. This is at a much lower frequency. So it's very safe to assume that this is minus 90. Next will be the phase added by the second pole. That number we do not know, so let's write the complete expression. That is minus tan inverse of omega u loop by P2. And what about the phase added by the RHP0? That will also be a minus tan inverse of omega u loop by Z1. So which means if I write the phase margin, the way I will see it is 180 minus the absolute value of this fellow, so that there is no confusion with negative signs. So that will give you 90 minus tan inverse of omega u loop by P2 minus tan inverse of omega u loop by 0. Okay. Whichever way you understand, it's fine. The way I will say it is, I'll look at the absolute value of the phase so that I don't get confused with the negative sign. I'll take 180 minus the absolute value of this phase. Okay. But whichever way you are comfortable with, please go on with it. Okay, so now let's simplify this. I have omega u loop. Omega u loop is beta gm1 by cc. The 0 location is gm2 by cc. I take the ratio of these two fellows. Cc goes off. So this I can further approximate as beta times gm1 by gm2. So again, you can see that now if you have RHP0, you want this term to be small or large? I mean, do you want the phase added by the RHP0 to be a small value or a large value? Small value, so that you have a large phase margin. So if that is the case, what can you say about GM1 and GM2? GM2 should be smaller than GM1 or GM2 should be larger than GM1? Is that okay? If GM2 is larger than GM1, only then this will be a smaller angle, you get a larger phase margin. So you straight away get a design guideline that if you have the RHP0, then you are better off choosing GM2 to be much greater than GM1. Is okay? Any confusion? I mean, this is the term due to the RHP0, right? That's what is this. I want to minimize this angle, so which means I should have a larger GM2. Okay. So let's take a simple example and see